Hi everyone. In this video, I will continue the discussion on the definitions in OpenSees with STKO. Previously, I discussed the definition on all these five friction models. Um, Today, I will discuss about the limit curves. This is going to be a very lengthy lecture, and um, this um, video, I will discuss about the limit state uniaxial material, the application of limit state material models, and discussing the shear springs in series model using hysteresis material model, as well as uh, shear critical column and the uniaxial material model. But the main thing is uh, the shear failure model and axial failure model. That what actually are these model, and the summarization is the modeling of the existing structures um, in this whole lecture. So why this rotation, sorry, the limit curve is included in the STKO, as well as why it is included in the definitions here. Uh, in the previous category for the friction models, um, we discussed these five terms, and in detail, I somehow explained how the syntax can be written for this environment. Um, and now, in this video, um, I am going to discuss the limit curve. So these two parameters, sorry, the categories, the friction model and the limit curve, their nature is different. So they are separated in this graphical user interface. The friction model is related to the definition of friction incorporation in the models for the definitions of the friction criteria, while the limit curves are totally related to the capacity of the model and validations of the results using the limit states based on which the degradation is introduced in the models. So we can call it whatever name we include here. Let's call it limit states here. So first thing that I need to mention here is that this modeling environment that we are using here, um, this requires some prerequisites in the STKO environment before discussing all these parameters, and that is the inclusion of the uh, hinges or nodes that are required, and the STKO, or even if you are working with OpenSeas, you have to define those tags. And in the definition, you will find out about these in a detailed way, that how you can include them. So, what's the reason of including the limit state curve for the rotation? Um, so it's very important to consider it. And even if you go to the OpenSees documentation, we have a discussion on these two parameters. The first one is the shear limit curve, and the second one is the axial limit curve. So these two are important as well, but um, they're not that much simple um, the way they look like here, because if we are diving into the limit curves for limit curves that we are discussing here, we need the limit state material objects and shear failure, and similarly for axial material we need the limit state material uh, categorization and or analysis. So also there is a detailed discussion on the reinforced concrete column by Ken Elwood, because he is the developer of this code. Also, various material models are combined, and those material models are being validated in the experimental work and numerical work we perform. So um, I think we need various kind of definitions to understand before just opening this software and defining these um, here in our analysis. So we have this limit curve. So for shear limit curve, uh, we need the other informations that are required in the OpenSeas, and uh, also there are various kind of definitions that this model is depending on. So it's not that simple. Um, we need to understand what's going on in the model, and we need to understand what actually is um, required in modeling these structures. So let's have a look at the discussion in a detailed way. So, for example, if there is an existing structure, let's assume there is a portal frame, and you have some sort of definition in terms of geometry with having some cross sections and reinforcement details and all those stuffs that are required for the experimental work, and you want to check the performance of this portal frame. So um, you need to model various parameters that capture the shear and axial failure for such models. For example, the column that exists in this frame structure. If we talk about this column, for example, if this one is considered here, so for this column, we need some sort of definitions for these parameters before defining the fiber section for this column and discussing it, because understanding these parameters Uh, Really important. Just it's not about you know discussing the graphical user interface and just putting A, B, C and getting X, Y, Z. Um, you have to manually understand everything before just modeling this column in the OpenSeas. So, if you are interested in shear failure, axial failure, if you are interested in um, beam column element, and if you are interested in failure surfaces and collapse mechanism and all those stuffs, then in that case, it's important to understand these parameters. So, based on the previous experimental research and post-earthquake reconnaissance surveys and experimental works and findings, uh, it's well understood that the columns with light and widely spaced transverse reinforcement are vulnerable to shear failure and in turn axial failure during earthquake analysis. And let's say if we have this column and we are kind of discussing this column capacity, so it will have some sort of limit states in terms of drift, which is force, rotation curvatures, and all those stuffs. Um, so, it's obvious if you are working with OpenSeas, we have to define those fiber sections in the column in terms of those limit states, and we have to assign those special elements at these hinges, the joints, to consider them, and if there exists some other failure mechanism that we are interested in, we can trigger the already those regions with zero length element. So, if we already have this kind of study performed, so based on the experimental data, the failure surfaces can be formed to define the onset of shear and axial failure of such columns in terms of capacity curves, and and we can also find out that after the response of the column that intersects the failure surface, the shear axial strength of the column begins to degrade at some point due to nonlinear behavior of the concrete. So, um, based on this inspiration, these limit states models are included in OpenSeas, and this lecture will introduce you to the uniaxial material model that incorporate the failure surface and the subsequent strain degradation. So either they can be used as a single element in terms of a spring for a uniaxial material, or it can be used with the inclusion of beam column element in series, and in this way it can be combined with the elements. So either it can be used as single element or it can be used as a combination with beam column elements. And when used in series with the beam column elements, so the uniaxial material adequately capture the response of the reinforced concrete column during shear and axial load failure, and you can then use this approach in your experimental studies to validate your models. You can also develop your own material based on multilinear approach in your analysis models and explore the various capabilities of OpenSeas in your analysis. So, That's why it's important to understand these terms and get the behavior based on the available data. And OpenSeas provide a very best approach to capture the performance based on these parameters. And before going into uh, various states of failures, let me discuss something about the limit states and uniaxial material failure model. So uh, let's assume that this is the failure surface curve of this column. So by limit state, a collapse limit state, we mean that if the certain response is achieved, so instead of going straight and resisting that, the OpenSeas based on the material parameter will trigger that limit state, and degradation will start in this model, and the failure will be activated in this model. So given such a definition for the parameters in a model, the researchers can evaluate the influence of column shear and axial load failures on the response of the building frame systems. And this lecture will describe how drift capacity models for shear and axial failure can be incorporated in an analytical model to detect and initiate that specific strength degradation of those column elements. So there are various kind of limit state surfaces that are available. You can you can find out them on Google's in various literature, right? So based on those limit states, we can relate the shear demand to the drift shear failure based on the transverse reinforcement and axial load ratio. Um, and and also we can find out the intersection of the idealized load deformation curve and the limit state surfaces defined by the capacity of the model, and we can study about those in our OpenSeas models. So based on those limit states, there are two important failure modes in limit surfaces uh, based on the axial model and axial load and shear loads here. So the first one and the second one, I will demonstrate those two here. So let's say we have that first one curve, and this is the shear demand curve, and we have in term of displacement or drift here, as is horizontal here. Um, Another one is for the horizontal drift, right? And um, with horizontal drift, the load is defined here. So the column will not only fail in shear in axial load capacity, but also shear load capacity. So a question may arise that why two curves are incorporated in this model, and why merging these two are required to consider in the OpenSeas. Um, and we have some predefined um, red line in term of the limit state that is required to consider in this model. So let's say we have this surface and we are telling the OpenSeas, if my shear is going to the right side of this curve, trigger the warning and collapse that member by its performance. Similarly, if the axial limit is going to cross this region, uh, and directing you to just trigger the warning and reduce its capacity. So this is the main concept here. And at certain point, the shear is increasing in its elastic range. Then plastic deformation occur, and after certain amount of plastic deformation, this region is trimmed from this model, and this will be considered as the total failure of this model in terms of shear. Similarly, if there is an axial force and that axial force reach to this region, the warning will be triggered, and based on this failure region, it will not resist that model. So if the and we have some sort of uh, relationship between the combination of these two. So if it is and why these two are important, why the combination is important, because if we have a column, we may need axial force definition, but there is a minor amount of shear failure. While if the member is thick and shear is dominant, then axial forces will be less here. We can consider the column with respect to shear wall. So that's why if the aspect ratio is smaller, we may notice the dominant failure mode in terms of shear and checking its performance. While if we have a slender or thin column or a long column, we may notice the dominant behavior in terms of axial failure here. So for shorter column, we may not achieve the axial force that will cross the limit surface defined by the axial capacity of the column. Rather than we will have a larger amount of shear, while for longer column we will have a smaller amount of shear and we will have a larger amount of axial force, and then this warning will be triggered here. So it's a sort of combination of these two models, and that's why I discussed this here to combine them in this modeling environment here. So the thing is, by combining these model uh, while describing different phenomena, the shear and the axial capacity that I discussed here in this model, both model define a limit surface and they trigger a change in the hysteresis behavior that we may notice in our model if earthquake load is applied in this direction. So, and how it work here. So, let's say we have this uh, FC sign ordinate in term of drift and shear P, whatever we are using here. So, in case if we trigger some sort of uh, cyclic loading in the hysteresis performance here, we notice this sort of uh, behavior, and this region that we are using here, this is basically due to that limit state that we are defining to our model, and that limit state that we are defining here actually define our curve. So sort of a complex mechanism we may notice here in this model, and we get our backbone curve. So this is an opportunity in OpenSees that uh, you can combine various kind of models and you can discuss them while describing the different phenomena. So it is important here. Um, Other than that, if we consider the limit surface for both axial capacity and shear capacity, um, capacity models are frequently used to determine uh, if components have experienced failure by comparing the predicted capacity with demand estimated from an analytical model. by using it with SAFe or ETABE or other software. So at this point in OpenSeas, it's possible to capture both the point request the failure as initiated and the response of the column of tertiary and axial load failure during analysis of the structure. So such a model enable the analysis of the structure system with multiple columns vulnerable to shear and axial failure as the structure system approach that collapse limit states here. So you might have noticed these failure modes, these limit states, and all these stuff in your model, and you will have a better idea of those limit states here. But behind the scene, those limit states, there is a definition of the uniaxial material model that may be um, concrete or maybe steel, and um, the joints mechanism in the discussion. So, this lecture I will discuss the general material model uh, that are proposed and implemented in OpenSeas for earthquake engineering simulations and the concepts behind these models. So, first, the concept of material model as they are applied in OpenSeas, I discussed them here, and then the available shear critical column models and some material models this lecture will cover, and the application of the material that I already discussed here. So first thing first, what is the uniaxial material model? What it does here? So the uniaxial material model define the constitutive relationship uh, and both in compression and tension. And depending on the applications, the material model could define the relationship between um, stress and strain, force and displacement, moment and curvature, moment and rotations, etc., etc. It depends on the available um, experimental work that is performed in OpenSeas, and this is the most simplified model in the OpenSeas environment. So it's kind of the lowest level of object that compose elements in OpenSeas, and one-dimensional elements such as springs and truss members require only one uniaxial material model to define their response here. So, for example, if we have a truss element, we only need one uniaxial material, or if we have a spring element that we want to define. So we need only one element to define them in terms of force, displacement, or stress strain, moment curvature, moment rotation response here. So we can in OpenSeas we can then take an idea from those elements and uh, get the response from those elements. So um, we can use them in this way, and you can imagine them like this. For example, if you have a rubber band and you are stretching it here, so at certain point you will be able to stretch it, right? But then after that you will not be able to stretch it, and it will either break, cut away, it will elongate. So that elongation can be represented in terms of stress strain, which indirectly is the definition of the material that you are using in the experiment element here. So it's kind of checking the performance based on the available information. Similarly, if you want to check the the strut time mechanism, or you want to check the compression tension behavior, you can use it in your analysis as well. So In OpenSeas, we have steel 01 elements, steel 02 elements, which incorporate further uh, parameters in our analysis. And one-dimension elements that I discussed here, the springs and truss elements, require only one uniaxial material to define their response. So uh, we can also use them for the zero-length spring elements and uniaxial material definition for the force displacement relationship directly. Um, in this lecture, the uniaxial material model that I am going to discuss are already available in OpenSeas, and the hysteresis material model. It is a predefined trilinear or bilinear backbone curve and some parameters to define the hysteresis behavior. And these parameters include either the strain degradations and strain degradation parameter that is very important, and I discussed this here as well in terms of triggering the warning to OpenSeas that if the limit is reached to its collapse, you have to trigger the warning and reduce its capacity here. And the shear critical columns as well, that is important here. So let me discuss the shear critical model before going to the discussion on the STKO if you are using the STKO environment here. So let's go to the um, next lecture and continue this lecture in the next video.